Welcome to the second lesson on Popper and the philosophy of science. Let's briefly recap the themes covered in the previous video. Karl Popper, an Austro-British philosopher, stands as one of the most influential thinkers of the 20th century. Born in Vienna in 1902, Popper's intellectual journey led him to grapple with fundamental questions about knowledge, science, and society. His work, characterized by clarity and rigor, revolutionized the philosophy of science and continues to shape contemporary thought. Popper's contributions are vast, but he is perhaps best known for his pioneering work on the nature of scientific knowledge. He challenged the traditional view of science as a process of verification, arguing instead that true scientific theories are those that are falsifiable, meaning they can be refuted through empirical tests. This idea, known as the principle of falsification, became a cornerstone of his philosophy and a defining feature of genuine scientific inquiry. Beyond his work on the philosophy of science, Popper made significant contributions to political philosophy, metaphysics, and the philosophy of mind. His defense of open societies, his critique of historicism, and his articulation of the theory of three worlds demonstrate the breadth and depth of his intellectual contributions. Popper's work is characterized by a profound commitment to reason, critical thinking, and the pursuit of truth. His ideas continue to resonate with philosophers, scientists, and thinkers across various disciplines, cementing his legacy as a giant of 20th century thought. In the following sections, we will delve deeper into Popper's key ideas, exploring their nuances and their lasting impact on our understanding of the world. At the heart of Popper's philosophy of science lies the concept of falsifiability. Popper argued that true scientific theories are not those that can be definitively proven, but rather those that are open to the possibility of being refuted or falsified through empirical observation or experimentation. This idea, known as the principle of falsification, serves as a key criterion for distinguishing true science from pseudoscience. According to Popper, a scientific theory must make specific and testable predictions about the world. If these predictions are confirmed by observation or experiment, the theory is corroborated but not definitively proven. However, if even a single observation or experiment contradicts the theory's predictions, the theory is considered falsified. This emphasis on falsification rather than verification stems from Popper's recognition of the inherent limits of inductive reasoning. Popper believed that no amount of confirming evidence can definitively prove that a scientific theory is true. There is always the possibility, however small, that future observations may contradict the theory. On the other hand, a single disconfirming observation has the power to definitively refute a theory. Therefore, for Popper, the hallmark of a true scientific theory is its willingness to expose itself to the possibility of falsification. The principle of falsification has profound implications for how we understand the nature of scientific progress. Science, according to Popper, does not consist of accumulating confirming evidence and building ever larger edifices of indisputable truth. Instead, it is a dynamic process of conjectures and refutations, where scientists constantly test existing theories, seeking to expose their weaknesses and replace them with better and more comprehensive explanations of the natural world. At the heart of Popper's principle of falsification is the concept of basic statements, also known as basic assertions or protocol sentences. These are singular and existential statements that describe specific, observable events or phenomena. Basic statements serve as the empirical foundation upon which scientific theories are tested and potentially falsified. A basic statement must be formulated in such a way that its truth or falsity can be determined through observation. For example, the statement, "This swan is white," is a basic statement because it can be verified by observing the color of the swan in question. If the swan is indeed white, the statement is considered true. If it is not, the statement is false. Basic statements play a crucial role in the process of scientific falsification. According to Popper, a scientific theory must be connected to a set of basic statements that describe potential falsifiers, that is, observable events or phenomena that, if observed, would contradict the theory's predictions. The more potential falsifiers a theory has, the more falsifiable it is, and therefore, the more scientifically valid it is. It is important to note that basic statements are not immune to errors or revisions. Observations can be influenced by various factors, such as the limits of our sensory perception or biases in our interpretations. However, Popper argues that basic statements can be intersubjectively tested and potentially corroborated through the agreement of multiple observers. This intersubjective verifiability distinguishes basic statements from subjective opinions or beliefs, which are not open to such public scrutiny. Contrary to the traditional view of science as a purely inductive process, Karl Popper proposed a deductive model of scientific discovery. He argued that scientific knowledge does not progress through the gradual accumulation of confirming evidence, but rather through a process of conjectures and refutations, often described as trial and error. Popper's approach begins with scientists formulating bold and imaginative hypotheses or conjectures about the world. These conjectures do not derive from observation or experience, but are the product of creative imagination. Once a hypothesis is formulated, scientists use deductive reasoning to derive testable predictions or falsifiable consequences from the hypothesis. These predictions are then compared with the results of empirical observations or experiments. If the predictions are consistent with the observed data, the hypothesis is considered corroborated, but not definitively proven. However, if the predictions are contradicted by the observations, the hypothesis is considered falsified and must be revised or abandoned altogether. This process of conjectures and refutations, of trial and error, is essential for scientific progress. By subjecting their hypotheses to rigorous tests and attempting to falsify them, scientists eliminate false theories and refine those that survive the process. Over time, this iterative process leads to the development of increasingly accurate and comprehensive explanations of the natural world. Popper's emphasis on deduction over induction stems from his belief that scientific knowledge does not derive from experience, but rather from our attempts to impose order and structure upon it. We do not passively observe the world and then derive theories from our observations. Instead, we actively engage with the world, formulating hypotheses and then testing them against reality. Reflections on the implications of Popper's thought on philosophy and metaphysics. The theory of the three worlds. Popper proposes a distinction between physical objects, subjective experiences, and the objective contents of thought. Popper also focuses on the theme of freedom and political philosophy, insisting on the defense of democracy while criticizing historicism. We will revisit these last two themes in the next video. Conclusion of this lesson. Popper's work is truly a timeless relevance. Thank you for your attention. The text is by Alessandro Benigni. Additional materials on Popper can be consulted and downloaded for free from the website integraciones.wordpress.com. See you in the next episode.